This is lesson 74 of our no-nonsense A-level physics lessons, Whiteboard Physics. And this one's all about making careful measurements. Well, first things first, what do you need to be able to measure with? What instruments do you need to be able to use? Instruments. Now, if there are any of these that you are not able to use, then you need to get your teacher to show you how to use them. And I would hope that most people could use a ruler. You should also be able to use vernier calipers. It's all very well having digital calipers, but vernier scales need to be read, and micrometers as well. Now, all of those micrometers, all of those are required according to the GCSE specifications. So if you've not been taught how to use vernier calipers or micrometers, well, now's the time to learn. You should already know. You would also need to use a balance. And there are different types of balancers: digital balancers, spring balancers, top pan balancers, I suppose we can call them, triple beam balancers, lever balancers. They all work the same basic way, and you do need to be able to use a balance to measure the mass of an object. You need to be able to use protractors. And you needed all of these so far are GCSE level stuff. There's nothing new here. Stopwatches or timers. So let's put stopwatch. Can I fit on the end? No, let's put it down here. Stopwatches or timers, digital timers, that sort of thing. You also need to be able to use an oscilloscope to measure times across the time base as well. Oscilloscope. I do a video about how to use oscilloscopes as part of this A-level series. I've already recorded it, but don't ask me which one it is. At some point in the waves section. You need to be able to use a thermometer. Digital thermometer, or one of the mercury or spirit thermometers. Mercury thermometers aren't so fashionable anymore, although I still use them. You need to be able to use ammeters and voltmeters. Now, ammeters have to be connected in series, and voltmeters have to be connected in parallel with the components we're investigating. But you've got to be able to use digital ammeters and voltmeters, and analog ammeters and voltmeters. Remember that a digital ammeter has very, very low resistance compared to an analog one, and a digital voltmeter is very, very high resistance compared to an analog one. So those are advantages of digital meters. The advantage of the analog meter is that you can make measurements in real time. You don't have to wait for the screen to refresh. Usually digital meters refresh every quarter of a second, third of a second, sometimes even every half a second. But if we're investigating discharge of capacitors, sometimes it can be useful to use an analog meter instead. That's pretty much it, let's say. There are some other things that come up here later on in the course, like you'd be able to use Geiger counters. But we'll come to that as and when we need it. Frequency meters built into multimeters, all that sort of thing. This is just a starting point. Some instruments that really you ought to be able to use when you start your A-level. Okay, so we make measurements. Our measurements must be valid. What does that mean? Measurements must be valid. Well, the word valid is a technical word. It has a technical meaning. It means that the data is useful for the investigation we are conducting. So to give you an example, if we were investigating radioactive decay, knowing the temperature of the room is a bit pointless. If we were investigating how the laser diffraction works, then knowing the, think of another one, knowing the current through the laser, actually not that interesting. So in order to be valid, it has to be useful for the, let's see if I can write this, I'm using the laggy pen because the other one just ran out. Now let's go back. Measurements must be varied. In other words, they must be useful for the investigation. You can measure all sorts of things that are completely pointless. But you've got to make sure you're measuring things that are useful. Resistivity, does it depend on pressure? Actually, yes, a little bit. Air pressure will affect resistivity in a sense, but not by any amount that makes it worth measuring. We wouldn't do anything with it in our investigation, so there'd be no point measuring it. Right, so repeatable and reproducible is next. The difference between reproducible and repeatable. So our measurements, they ought to be repeatable. So what does that mean? So that means that we get the same results if done the same way. So repeatable results. Repeatable results, which means we get same results, or close enough to them, within experimental error. Within experimental error when measured with same apparatus in the same way, same methodology. That's what we mean by repeatable. Reproducible, not to be confused, reproducible results, they can be obtained, same results, but using different instrumentation, different methodology. Same results with different instrumentation or methodology. And you wouldn't necessarily test that yourself. That would be another team that would have to test that. Make sure your results are repeatable by taking repeats. In terms of reproducible, no, that's harder for us to actually find out. So that's why we have peer review and stuff like that. Now, I mentioned errors before. I said within experimental errors. Errors are not mistakes. Errors are things that cause results to have a small variation. So there are different types of errors, but errors are not mistakes, not in physics. We often see people saying, oh, name an error in this experiment. Oh, human error might change the results. No. When you say human error, what you mean is a human has made a mistake. Errors are not mistakes. That's a colloquialism, and it is wrong. So there are different errors that we need to be aware of. There is this systematic error, which we always have to be aware of and careful of. Systematic errors. These are caused usually by some way in which the experiment is being performed. Usually caused by instrumentation or methodology. They can't always be helped, so don't think it's a mistake. Instrumentation or methodology, and you can account for them if they can be measured. If systematic error can be measured, why have I written can twice? Can be measured, it can be removed. So what does that mean? Well, you always subtract your systematic error. So if your systematic error means that every length is 2 millimeters too long, then you subtract that systematic error of 2 millimeters from all your lengths before you do any other processing. If your timer, there's some issue with the timer and all of your times are 10% too long, well, then you can remove that 10% from each of those measurements before you do any processing. So systematic errors are the same amount each time. We should say the same bias for each measurement. Same bias for each measurement, and you subtract that bias. Random errors are harder to deal with. This is just whatever causes a spread of results, or spread of measurements, should I say. A spread of measurements for a single measurement. Spread of values for a single measurement, let's say that. And it won't be a big spread. The smaller the spread, the better. But this is what random errors are. So spread of values. And actually, that's something you can't help. If I measure my height, I'm 2 meters tall. I'm 199 centimeters tall in the morning and 198 centimeters tall in the evening. So if I measure myself first thing when I wake up, I'm a little bit taller, and last thing at night, I'm a little bit smaller. And if I were to take some random measurement of my height at a random point throughout the day, it's going to be somewhere between them. There's going to be a spread of results. Now, you could argue that that is actually a systematic error because there's a pattern to it, there's a bias to it. And I'll accept that. But if you're measuring my mass, that would be much harder. There's some pattern. After I eat, it goes up a little bit. And just after I have defecated, it goes down a little bit. But let's be honest, it fluctuates all over the place with no real pattern most of the time. Right, so that's our random errors. And remember, errors are not mistakes. So there's no bias, there's no pattern to our spread of values. Then it's caused by just the fact that values often have a spread. So when we record our measurements, we have to record an uncertainty. Uncertainty in our value must be recorded for every measurement, if possible. I say must be, but it might not always be possible for every measurement. And that's where the average value becomes important later on, because you'll have a few different values. If you remember last lesson, we sort of set out a table like this. We said we might be measuring the wire diameter a few times and then calculating an average, but that average should have plus or minus some uncertainty. Our average should have plus or minus some uncertainty. That uncertainty won't always be the same for every measurement. I'll actually leave these in these notes, even though this last lesson's notes must be recorded for every measurement. So yes, we will always have plus or minus an uncertainty. And how do we calculate the uncertainty? Calculated as half of the range of values. Now that is how we calculate them in A-level. There is a better way of calculating uncertainty, which is the standard error. And there's different ways of calculating standard error, either standard deviation divided by the number of measurements minus 1, or the standard deviation divided by the number of measurements minus 2, depending on whether the number of measurements is of a population or of a sample. And it's a very big subject. Calculating uncertainties is an enormous subject, which we don't really need to go into at this stage. So plus or minus, which means the real value is within a certain range, and that range is half of the range of values, is a good enough way of approximating our uncertainty. And the good people at different exam boards have determined that if you make 7 measurements, then the chances are the very thorough way of calculating uncertainty will most closely match this very quick, rough and ready half the range of values measurement. Too few values, and then our standard error calculated the proper way is actually a bit smaller than it should be. Too many, sorry, is a bit bigger than it should be. Too many measurements, and it goes a bit smaller than it should be. If we plotted a graph, and I will erase this, so don't copy this yourself, but I've plotted a graph of number of measurements versus the uncertainty. I'll just use an epsilon for error there. The uncertainty, then obviously you would expect the more values we take, it would actually have the risk of increasing the range. So that is using the quick method of half the range. But if we use the proper method, it actually does this. That's the proper method that we use at university level, proper method. And it turns out people who have done the investigation with A-level experiments, it tends to be around 7 measurements is where they're as close as possible, usually. I'm trusting what I've heard and read. I've never actually tested that myself, although I'm tempted to do so. Maybe I'll record a video called Why 7 Values. But I haven't done that yet. I haven't had the time. I'm not convinced it would be true anyway, but there we go. So 3 measurements is fine, but 7 is better. Right, so that's uncertainties, which are part of errors. It's the uncertainty is the number that we write that tells us the range of values that we would think of as the real value, what we call the true value, being somewhere within that. So going back to our diameter thing, I might have a diameter of, let's say an average diameter might be equal to 0, let's say 1 point, let's say average diameter divided by millimeters, so it's a little bit easier, might be equal to 1.01 plus or minus 0.10 or something like that. And we can, well, we probably wouldn't write it quite like that, but we can talk about that and uncertainties when we do real practical work. Now, I have recorded a video all about uncertainties as part of my Transition to A-Level series, the 6 videos with topics that I think all A-Level students should know before they start their A-Level. I tell my students to watch them over the summer before they start A-Levels and to answer some questions about them. And it's very important that they do that. If you're not one of my students in a school, if you're someone out there in the wild, then I would recommend you watch those right at the start of the course anyway. Well, this is lesson 74, so if you're watching these in lesson order, it might be a bit late by now. Right, so zero error. I mentioned zero error. What is it? Zero error is where your instrument is not correctly calibrated. And so it shows a value when it should show 0. And when that happens, we just have to subtract that value. So instrument, we treat it like any other systematic error. It is a type of systematic error. So instrument shows non-zero value. It could be a negative, could be a positive, when should show 0. And we deal with that by subtract the 0 error. That means we need to measure the 0 error. So for things like vernier calipers or micrometers, subtract 0 error. I don't know why I keep on rubbing out. 0 error. For things like that, for instruments like that, we would measure what the 0 error is, write that down in our investigation, and then we stop flipping around. And then we could delete that. We could subtract, not delete, we could subtract that 0 error from every measurement we take. It's important to record it. Right, uncertainty we've already talked about, so I'm not going to go into that. Accuracy then. What do we mean by accuracy? Accuracy is how close a value is to the true value. how close a measurement is to the true value. It used to be called the accepted value, but they've changed the name of that. So accuracy, how close a measured value is to the true value, which used to be called accepted value. True value. That we don't call it accepted value anymore, which is rather frustrating. And that's it. So your uncertainty is a measure of the accuracy. The larger the uncertainty, the lower the accuracy. Right, next we can talk about precision. Now, it's impossible to determine precision if you only have one measurement of something, because this is about the spread of measurements. Or it could be the spread of readings as well, which I won't get into the difference between measurements and readings just at this point. So spread of, let's say, readings. So smaller spread means more precise. Like that. Now, it used to be that precision was the number of decimal points you recorded your instrument value to. We don't have a fancy name for that anymore. So this is what we call precision. Now is the spread of readings. Now you're going to say, well, how is that different to uncertainty? Well, because with precision, we are talking about readings off an instrument, not just any value such as calculated values. Uncertainty is of any value, including calculated values. So I suppose the uncertainty of a reading is the precision of that reading. But you can only tell that if you've got lots of values recorded. Whereas uncertainty of other things, measurements, which are usually the difference between two readings, that's what a measurement is. What's the length of something? It's the reading of the ruler at one side to the reading of the ruler at the other side, the difference between them. So measurements involve two readings. But then you can have anything. So if you're measuring or determining the resistivity of a wire, as the example I've been using, then you're measuring it. That's a measurement. You can have an uncertainty to that value, but you wouldn't say there's a precision to that value. Precision is associated with measurement. And it's closely linked to the idea of resolution. And the resolution of an instrument is the smallest measurable interval. Interval. So for a ruler, it's usually 1 millimeter, 0.001 meters. For a micrometer, it could be 0.01 millimeters, or for a vernier caliper, it could be 0.1 millimeters. So that's resolution. A couple of other terms we need to understand. I'm not going to talk about instrument range because I've talked about that before. Linearity, if our results, if our meter is a linear scale, then as the value it measures goes up, a needle might move across linearly to it. Don't really need to talk about that at this stage. And I don't want to get into specifics about how to use instruments at this stage. So that'll do for now. Making careful measurements. The key thing here is take as many repeats as you think is appropriate and record those errors. Record them. It'll be very important. Right, okay. That's it for this lesson.